The Inverse Cube Force Law by John C. Baez. I'm Dr. Samuel Allen Alexander, mathematician and philosopher, still here, and I'm reading this article published this year in the Notices of the AMS. Newton's Principia is famous for its investigations of the inverse square force law for gravity. But in this book, Newton also did something that remained little known until fairly recently. He figured out what kind of central force exerted upon a particle can rescale its angular velocity by a constant factor without affecting its radial motion. This turns out to be a force obeying an inverse cube law. Given a particle in Euclidean space, a central force is a force that points toward or away from the origin and depends only on the particle's distance from the origin. If the particle's position at time t is r of t in real n space and its mass is some number m bigger than 0, we have m times the second derivative of r at t equals force of r of t times r hat of t, where r hat of t is a unit vector pointing outward from the origin at the point r of t. A particle obeying this equation always moves in a plane through the origin, so we can use polar coordinates and write the particle's position as r of t theta of t. With some calculation, one can show the particle's distance from the origin r of t obeys m times the second derivative of r of t equals force of r of t plus big L squared over the m times that cube of r of t. Here, big L equals m times the square of r of t times the derivative of theta of t. The particle's angular momentum is constant in time. The second term, big L squared over m times the cube of r of t in the equation, says that the particle's distance from the origin changes as if there were an additional force pushing it outward. This is a fictitious force, an artifact of working in polar coordinates. It's called the centrifugal force, and it obeys an inverse cube force law. This explains Newton's observation. Let us see why. Suppose that we have two particles moving in two different central forces, F1 and F2, each obeying a version of the equation above, with the same mass m and the same radial motion r of t, but with different angular momenta L1, big L1 and big L2. Then we must have force 1 of r of t plus big L1 squared over m times the cube of r of t equals force 2 of r of t plus big L2 squared over m times the cube of r of t. If the particle's angular velocities are proportional, then big L2 equals k big L1 for some constant k. So force 2 of r1 of t minus force 1 of r of t equals k minus 1 quantity big L1 over m times the cube of r of t. This says that force 2 equals force 1 plus an additional inverse cube force. A particle's motion in an inverse cube force has curious features. First, compare Newtonian gravity, which is an attractive inverse square force. Say force of r equals minus c over r squared with c bigger than 0. In this case, we have m times the second derivative of r at t equals minus c over the square of r of t plus big L squared over m times the cube of r of t. Because 1 over r cubed goes faster than 1 over r squared as r goes down to 0, as long as the angular momentum big L is non-zero, the repulsion of the centrifugal force will beat the attraction of gravity for sufficiently small r, and the particle will not fall into the origin. The same is true for any attractive force. A force of r equals minus c over r to the p with p less than 3. But an attractive inverse cube force can overcome the centrifugal force and make a particle fall into the origin. In fact, there are three qualitatively different possibilities for the motion of a particle in an attractive inverse cube force. Force of r equals minus c over r cubed, depending on the value of c. With some work, we can solve for 1 over r as a function of theta, which is easier than solving for r. There are three cases depending on the value of omega squared equals 1 minus cm over big L squared, vaguely analogous to the elliptical, parabolic, and hyperbolic orbits of a particle in an inverse square force law. 1 over r of theta is big A cos omega theta plus big B sine omega theta if omega squared is bigger than 0. 1 over r of theta is big A plus big B theta if omega equals 0. And 1 over r of theta is big A e to the abs omega theta plus big B e to the minus abs omega theta if omega squared is less than 0. The third case occurs when the attractive inverse cube force is strong enough to overcome the centrifugal force, c bigger than big L squared over m. Then the particle can spiral into its doom, hitting the origin in a finite amount of time after infinitely many orbits. An example is shown in Figure 1. All three curves are called Coates spirals after Roger Coates' work on the inverse cube force law published posthumously in 1722. Coates seems to have been the first to compute the derivative of the sine function. After Coates' death at the age of 33, Newton supposedly said if he had lived, he would have known something. The subtlety of the inverse cube law is greatly heightened when we study it using quantum rather than classical mechanics. Here, if C is too large, the theory is ill-defined because there's no reasonable choice of self-adjoint Hamiltonian. If C is smaller, the theory is well-behaved. But at a certain borderline point, it exhibits a remarkable property: spontaneous breaking of scaling symmetry. I hope to discuss this in my next column. Interesting. The author leaves us on a cliff's note. This is a very famous author online these days. Recently, he writes a lot of articles that a lot of people cite. Yeah, there's a lot of hidden gems in Newton's Principia. I read the whole thing cover to cover a few years ago, and most of it went over my head as expected. But I like to read important things, even if they go completely over my head, because I feel like my subconscious mind derives value from them. The same way that we don't remember the things we ate many years ago, but those things that we ate nevertheless build us up and constitute us. I'm Dr. Samuel Allen Alexander, mathematician and philosopher. Please like, comment, and subscribe. I'll see you in the next video.